Hi all. I apologize for not being able to be there tomorrow, but I wanted to go over these practice problems with you because from what I was seeing you guys work in class, there are some things that we need to clear up. Okay, so let's go over these practice problems from 11.1 in detail. So first of all, we want to list the first 5 terms of the sequence for number 1. And so my sequence is going to be, when you plug in 1, that's 1 over 3 plus 1, which is 1/4. 2, 1 over 9 plus 1, it was 1/10. Let's see, 1 over 28. Right? And if I think about it, it might be helpful to say, okay, if I start at 1, that's 3, 9, 27, 81, and 243. So that my denominators are going to be 1 more than that. So 4, 10, 28, 1 over 81, and 1 over 243. So on and so forth. Oh, wait, 244. Nope, got to change both of these. Got carried away. Got to add 1. So 82 and 244. Okay, so those are the first 5 terms for that sequence. For this one, my AN. All right, let's see. Negative 2 to the 1 is negative 2. 1 plus 1 is 2. 2 factorial is 2. 2, plug in 2. We get negative 2 squared is 4 up top. And then 2 plus 1 is 3. 3 factorial is 6. Plug in 3. Negative 2 cubed is negative 8. 3 plus 1 is 4. 4 factorial is 24. Now you can start to see what's happening here. You're multiplying by negative 2 up top. So negative 8 times negative 2 gives me 16. And the last one is going to be negative 32. And on the bottom, I'm multiplying by the next number. So the next number from 24 will be to multiply it by 5. So that's 120 and then 720. You can check if you plug in 5, negative 2 to the 5th would be negative 32. 5 plus 1 is 6. 6 factorial is 721. Okay, so that's the first 2, or you're listing out the first 5 terms of the sequence. Okay, nothing crazy there. Now we want to find the general form for the following sequences. Okay, so what I like to think about doing here, when you've got things that don't match up, so these first 2 terms here do not look the same as the next 3. So I'm going to think about what would I write for the next 3, because more of them are going to be like the last 3 than the first 2, right? Because as you keep going, it's going to look more and more like these fractions. So first we have the sum n equals 1 to infinity. And first of all, it's alternating. So I'm going to have a negative 1. And I need that to start with positive. So I'm going with n plus 1 on that one. And on the bottom, if I ignore those first 2, looks like I have powers of 4, right? And when I plug in 3, when n equals 3, I have to get 4 to the 1. So my exponent is 2 less than my n. So that means my exponent should be n minus 2. And then we can check to see if it works. So if I were to plug in n equals 1, I would get negative 1 squared over 4 to the negative 1, right? What that means is the 4 would come up, and negative 1 squared is positive. So positive 4 checks out. N equals 2. If you plug in 2, 2 plus 1 is 3. So that gives me a negative 1 up top. And then we're doing plug in 2. 2 minus 2 is 0. 4 to the 0 is just 1. So I get negative 1, and that checks out as well. Okay. So I like to think if the first 2 don't look the same, try to look at what's after that and then kind of map it back and make sure it works. Okay. Down here in number 4, if I look at the difference, I'm adding 3 each time. So that means I'm going to have the sum, n equals 1 to infinity. And I'm going to go 3n. And then what do I need to add if I plug in 1 to get 5? If I plug in 1, I get 3. So I've got to add 2 to get to 5. And again, you can check some of the other numbers. So those are our 2 where we are writing the general form. Okay, so we need to be able to write the general form and get the values. Next, do the following sequences converge or diverge? Okay. When you're going to talk about convergence, you have to explain why you're getting your answer. Okay, so you're either using some sort of mathematical technique or you've got some rationale as to why this works. Okay, so you've got to essentially be able to prove it. The way we typically do that is by looking at the limit. So in order to show whether this is going to converge or diverge, we're going to take the limit as n goes to infinity of an, which is 5 over n plus 2. When you plug in your infinity, this is 5 over infinity, which is 0, which means that it converges. Okay, so 5 is good to go. Number 6, same thing. We're going to take the limit as n goes to infinity, n to the 4th over 2n to the 4th plus 5. This one, when you plug in, is infinity over infinity. So you've got two options. One, you could use L'Hopital's rule. In that case, it would look something like this. So this is by L'Hopital's rule, this is the limit as n goes to infinity. And L'Hopital's rule just says we take the derivative of the top and the derivative of the bottom. So this would be 4n cubed over 8n cubed. And that turns out to be the limit as n goes to infinity. The cubes are going to cancel. And that's just 1/2. So you get 1/2. And therefore this converges. The other option is say, hey, we have a rule. When we have a polynomial divided by a polynomial, we take a look at the powers. And when they're balanced, you take the ratio of what's in front. So again, you get 1/2. Okay, so just two different ways to get 1/2. But when you get the limit equals 1/2, it tells you that this sequence converges. Okay. Here we go. Here's some more. Determine whether the sequence converges or diverges. Okay, so this one, again, I'm going to take a look at the limit. The limit as n goes to infinity of 4 to the n over 1 plus 9 to the n. This, of course, is infinity over infinity. So I'm going to take a look at L'Hopital's rule. By L'Hopital's rule, the derivative of an a to the n is a to the n times the natural log of a, so times the natural log of 4. On the bottom, the 1 doesn't have any derivative, or its derivative is 0, and then we get 9 to the n times the natural log of 9. And then I'm going to separate this and make it 4 over 9 to the n, and then we have the natural log of 4 and the natural log of 9. Now, the natural log of 4 over the natural log of 9, this is just a constant, so we're really concerned about what happens here. And remember that when we have a rule about this. We took a look at this. When you have a sequence or a limit, in this case, where you have r to the n, where r is between 1 and -1, then this converges. Okay, and that's what's happening here. So we have 1 over n. Okay, so that one's going to converge. Next, number 8, same kind of thing. We want the limit as n goes to infinity. The natural log of n squared over n. Again, this is infinity over infinity. So let's use our L'Hopital's rule. So let's see on the top. First, we have the limit as n goes to infinity. Derivative on the top is 2 times the natural log of n times 1 over n. Derivative of the bottom is just 1. So we can rewrite this as the limit as n goes to infinity of 2 times the natural log of n, and then 1 over n is the same as an n moving to the bottom. Okay. Now, if we plug in our infinity, this is infinity over infinity again, so we can use L'Hopital's rule again. And that's the limit as n goes to infinity of 2 times 1 over n all over 1, and when you plug in your infinity there to 2 over n, it becomes 2 over infinity, which is 0. So this one also converges. Okay, so L'Hopital's rule is your friend, and show that it converges or diverges using limits. Okay. Now for number 9, we have a theorem that says that if the limit of n goes to infinity of the absolute value of an is 0, then the limit as n goes to infinity of an is also 0, right? And it converges. Or we know that if the absolute value converges, then the sequence converges. So that means that I can eliminate the -1 to the n up top, and I can just look at this an as if the absolute value, meaning that we take away the negatives. Okay, so then we want the limit as n goes infinity of absolute value of an, which is the limit as n goes to infinity of absolute value of negative 1 to the n over 2 to the square root of n. The absolute value is going to take care of that negative 1 to the n. So this is just the limit as n goes to infinity of 1 over 2 square root of n. In that case, your infinity goes on the bottom and you get 1 over infinity, and that's equal to 0. So this one converges. So because the absolute value converges, when you let the signs alternate, it also converges. Okay. On to number 10. You've got n squared times e to the minus n. We take the limit as n goes to infinity of n squared e to the minus n. I want to make this look like a fraction because right now this one goes to infinity and this one goes to 0, and that's an indeterminate form. So we're going to take our limit as n goes to infinity, and I'm going to make it into a fraction by moving the e to the bottom. Now I get something that's infinity over infinity, so now I can use L'Hopital's rule. Because of the square on top, you're going to need to use it twice. So this is 2n over e to the n. Still infinity over infinity, so I use L'Hopital's rule again. So this is the limit as n goes to infinity of 2 over e to the n. This will give you the 2 over infinity. That gives you 0. So this does converge as well. Similar situation in 11. Sign's going to oscillate. The n goes to infinity. So you want to take a look at the limit. We want to use L'Hopital's rule here, so I'm going to keep the sign of 1 over n on the top. And I'm moving the n to the bottom. So the n is currently on the top with a positive 1. If I move it to the bottom with a negative 1, that's n to the negative 1, but that's just 1 over n on the bottom. And that way, when I use L'Hopital's rule, I have the limit as n goes to infinity. And that's the cosine of 1 over n times the derivative of 1 over n, which is negative 1 over n squared. And on the bottom, the derivative of 1 over n is negative 1 over n squared. So those two pieces cancel, and I'm left with just the limit as n goes to infinity of the cosine of 1 over n. Now we know that the cosine of 1 over n, as you go to infinity, 1 over infinity is 0, so this is equal to the cosine at 0, which is 1, and therefore this is convergent as well. Okay, so in moral of the story, when it comes to sequences, the key thing is that you're always going to look at the limit. You always look at the limit, you know you're going to get things right. Next, we need to determine whether our sequence is increasing or decreasing. Okay, the thing is here, what we know by definition is that a sequence is increasing or decreasing if the next term is larger or smaller than the previous term for all n. Okay, you can't just pick 2 and say, hey, guess what? These 2 happen to work. You got to show me that it works in general. So when I'm looking at 1 over 2n plus 3, if I look at the first 2 terms, when you plug in 1, that's 1/5. And when you plug in 2, that's 1/7. So this should be decreasing. Right? As our denominator gets bigger, this should go to 0. Okay, so we want to show that it's decreasing. So I want to show that that this term is greater than the next term. Right? They get smaller as I go. So as my n's get larger, the values get smaller. So if you plug that in, so an is 1 over 2n plus 3. And an plus 1 is 1 over 2 times n plus 1 plus 3. Okay, and I'm going to work this until I get something that's very obvious. Okay, you got to be able to convince me that what you have is true. So I'm going to simplify that. So 1 over 2n plus 3 greater than 1 over 2n plus 5. And I'm going to multiply both sides by 2n plus 3 and 2n plus 5. So that's going to give me 2n plus 5 is greater than 2n plus 3. And then if you subtract 2n from each side, you get the 5 is greater than 3, and that, of course, is true. Okay, so I went all the way until I had an obvious statement. And therefore, you can say that it is decreasing. Okay, you've got to prove it. All right, now this one, when you have n times negative 1 to the n, this is going to alternate. This one is going to infinity. So you're essentially going like this. Your an is negative 1, 2, -3, 4, -5, 6, etc. So your odds are going to go to negative infinity. They're decreasing because they're negative. And the evens are going to go to positive infinity, and those are increasing. So what you need to say is that they don't, both of them don't do the same thing. This is going to diverge like a fork. And so this is neither. It's neither increasing nor decreasing. Okay, that's totally possible. Okay, what about this one? This one starts at 2, and then you're adding on terms here. So when I plug in 1, I'm going to have 2 plus -1. So that's 1. And then when I plug in 2, I'm going to have 2 plus 1 half. So 2 plus 1 half. And that is going to be, we'll just call it 2.5. When you plug in 3, it's going to be 2 plus -1 over 3. And so 2 plus -1/3 is going to be less. That's going to be 1 2/3. And so now you can see I'm going up and then I'm going down. So this is also a neither. Typically, when you see the -1 to the ends, something that's going to change sign, that's typically going to create something that bounces around for you. It goes up and then down and up and then down. Okay. The last thing we want to do is determine whether the sequence is convergent by the MST. So this is the monotonic sequence theorem. The two pieces here, you have to show that it's bounded, so it lives between two numbers, and that it's either increasing or decreasing. Got to show both. Okay, so how do we do that here? First thing I'm going to do is rewrite this as n squared over e to the n. Okay, and we want to see what happens here. So if you think about this, n squared on the top, e to the n on the bottom. E to the n is much more powerful exponential than a polynomial, so that's going to pull it down to 0. So this should be decreasing. That's what we want. Let's look at the first few terms to make sure. So if you plug in 1, that's 1 over e. If you plug in 2, that's 2 over e squared, right? And 1 over e is about 1 over 2.7, so this is maybe a little less than a third, so a little more than a third, so maybe 0.7-ish. This is 2 over 2.7 squared, and 2.7 squared is bigger than 2.5 squared, and 2.5 squared is more, let's see, 2.5 is 5 halves, and that's 25 over 4, so that gets big real quick. So this, you have 2 over that number, and so this is going to be decreasing. If you put those two into a calculator, which we could do real quick, but we won't. But we can show that it's decreasing. So what I want to show is that an is greater than an plus 1. Right? It's getting smaller. All right, so then an is n squared over e to the n. An plus 1 is n plus 1 squared over e to the n plus 1. And this is one where I think it's not obvious that this actually is true, okay? So let's simplify a little bit. So n squared over e to the n. On the right, if you square that out, that's n squared plus 2n plus 1. On the bottom, that's e to the n times e. So the first thing that I can do is I can multiply both sides by e to the n. And that will cancel out what's in the denominator. So that's n squared is greater than n squared plus 2n plus 1 all over e. Then what we want to do is multiply both sides by e to get out of this e situation. So we're multiplying both sides by e. And that's going to give you en squared is greater than n squared plus 2n plus 1. Now, what I want to do, let's see, what do we want to do? From here, you're going to subtract to get common e's. So I'm going to subtract n squared from both sides. So that's going to give me en squared minus n squared minus 2n plus 1 greater than 0. So this is what I'm trying to show. And this is e minus 1 n squared minus 2n plus 1 is greater than 0. Okay, so what we want to be able to show is that this is true. So it gets a little bit complicated showing that some of these are true. Now, why should this work? I also have a negative in the wrong spot. Let me fix that. Okay, now I'm hesitating a little bit here because there are obvious ways that I can show this, but they're not quick and easy. I'm trying to think if there's a quick and easy way to go about this. So let's just do it. So what I'm thinking here is that this has to be a parabola that opens up, right? So if I'm trying to show that this is greater than 0, this is a parabola that opens up. If part of this is negative, right, meaning this is not greater than 0 all the time, so there would be a section that goes below, which means I should have 2 points that cross at 0. And if I don't, then it's got to be above, right? Because it opens up and goes all the way to infinity. If it's going to be less than 0, there's going to be a point where it's equal to 0. So let's see. If we did that, then we would have that n equals negative b, which would be 2, plus or minus the square root of 2 squared, which is 4, minus 4ac, but that's a plus because I have a minus here. E minus 1 squared all over 2 times e minus 1. Okay. All right. So what is this? Let's calculate it real quick. If I go and plug this in somewhere, e minus 1 is just a number. In fact, we could just kind of pull this up on a graph. All right, here's mu from alpha. So if you have e minus 1 n squared minus n minus 1. Why does it look like that? Equals 0. Okay, now notice what's happening here. They show us a graph and they show us where those 2 points are. What you want to notice is that this is only less than 0 for values of n that are less than 1, right? So once we hit 1 and move to the right, the values of this parabola are always greater than 0. Okay, so this is less than 1. And therefore, our n starts at 1 and goes up. So this is true for n greater than 1, greater than or equal to 1. And therefore, we can say that it is, in fact, decreasing for n greater than or equal to 1. Okay. The other thing we've got to be able to say here is that this is bounded. Right. And so what we can do here is say, well, when you look at n squared over e to the n, this has to be greater than 0. Right? Squares and e's are always positive. When you divide them through, they're going to be at least 0. But we also know that n squared is less than e to the n. And you can show that by saying, okay, here's n squared, and e to the n starts at 1 and goes up very quickly. So e to the n is always greater than n. So this is also true. And so that tells you that this is always going to be less than or equal to 1. The denominator is always going to be larger. And so this shows that it's bounded. And this shows that it is decreasing. And so by MST, it converges. Remember that the monotonic sequence theorem says that if it's bounded and monotonic, meaning either increasing or decreasing, then it converges. And then lastly, Number 16, you have n plus 1 over 3n plus 2. So same kind of thing. We need to show that this is either increasing or decreasing and that it's bounded. Let's start with bounded because that's easier. So let's show that it's bounded. So you have n plus 1 over 3n plus 2. And in that case, this has to be greater than 0 again, right? And that is because you have n's that are positive. You're multiplying by a constant and adding 1 everywhere, so you don't get any negatives. The next thing we also want to show is that this is less than or equal to 1. Okay, so we want to show that n plus 1 is always less than or equal to 3n plus 2. And you can do that just by solving this. So if we subtract n from both sides and subtract 2 from both sides, that gives us negative 1 is less than or equal to 2n. So divide by 2. And so this statement that we wrote right here is true for all n greater than or equal to, if I flip it around, negative 1/2. And because our n starts at 1, that works for us, right? We only have to know that it's true for n greater than or equal to 1. Okay, so that's true, and we can say that it's bounded. Next, we want to show that it is decreasing. If you plug in 1, you get 2 over 5. If you plug in 2, you get 2 over 7. Nope. 3 over 7. If you get common denominators there, that's 14 over 35 and 15 over 35. And so you can see that it is... Oh, wait, hold on. I did something wrong there. 8. It's over 8. Let's try again. The first term, when you plug in 1, 1 plus 1 is 2. 3 plus 2 is 5. When you plug in 2, 2 plus 1 is 3. 2 times 3 is 6 plus 2 is 8. There we go. Now you're talking about 16 over 40 and 15 over 40. And you can see that it's getting lower. So it is, in fact, decreasing. And so we want to show that n plus 1 over 3n plus 2 is greater than n plus 1 over 3 times n plus 1 plus 2. So this is n plus 1 over 3n plus 2. And you have n plus 2. If you distribute that, that's 3n plus 3, so that's 3n plus 5. Okay, so now what we want to do, multiply both sides, or essentially cross multiply here. Multiply both sides by the denominators. So if you multiply everything by 3n plus 2 times 3n plus 5. What happens is that you get n plus 1 times 3n plus 5 on the left, and you have n plus 2 over 3n plus 5 plus, 3n plus 2, the 3n plus 5 cancels on the right. Multiply this out, this is 3n squared, plus 3n plus 5n is plus 8n plus 5. And over here you have 3n squared plus 6n plus 8n plus 4. And if you can subtract 3n squared minus 8n from both square sides, you end up with the statement that 5 is greater than 4, which of course is true. So this shows that it's decreasing. And if I could spell decreasing, we would be good to go. There we go. And because it's bounded and decreasing, then by MST, it converges. Okay, so those are all the things that you need to show. So this is a little bit very rigorous. You've got to prove things to me from here on out in chapter 11. So you just can't state things. You need to be able to prove things. So make sure that we're doing that.